In this lecture, we will discuss some basic concepts in statistics. What's the meaning of statistics? If you check a dictionary, there are two common meanings for the word statistics. In the first meaning, statistics are the numerical statement of facts capable of analysis and interpretation. Or simply, statistics are a collection of quantitative data. They are usually organized and summarized to provide useful and accessible information about a particular subject. For example, the government regularly publishes the unemployment rate. It is a typical example of statistics. In the second meaning, statistics is a discipline of science. It is the practice or the study of collecting, presenting, analyzing, and interpreting numerical data, especially for the purpose of inferring population in a whole from those in a representative sample. In this definition, we highlight two words, population and sample. They are the important concepts in statistics. We will discuss them in more detail in a while. Right now, it is enough to know that statistics is the science about data. If we combine two meanings together in one sentence, we may say that statistics is a science on statistics. Let's look at these two examples. We want to use these two examples to demonstrate the difference between two branches of statistics, that is, descriptive statistics and inferential statistics. In the first example, 1948 baseball season. In 1948, the Washington Senators played 153 games, winning 56 and losing 97. They finished the seventh in the American League and were led in hitting by Bud Stewart, whose batting average was .279. If you read this paragraph, you may notice that there are many numbers. Those numbers are calculated from some raw data. Those numbers give us a clear picture about the performance of the team in one season without referring to the messy raw data. This is an example of descriptive statistics. Its focus is summarizing. The second example is about the 1948 presidential election. In the fall of 1948, the Gallup poll taken just prior to the presidential election predicted that President Truman would win only 44.5%. But the prediction was wrong. Truman won more than 49% of the vote. The focus of this study is not summarizing but predicting. In a typical poll, the statisticians will interview a selected group of people and ask their opinions. They hope that the opinion of this small group of people is similar to the whole population of voters. It is an example of inferential statistics. For inference, here, we mean that we want to generalize the information or knowledge we gain in a small group of people to a larger group of people or the whole population. Descriptive statistics consists of methods for organizing and summarizing information. We may use graphs, charts, or tables to present the information. We may also use numbers such as average, median, or percentile to characterize the features of the data. The inferential statistics is quite different. Inferential statistics consists of methods for drawing and measuring the reliability of conclusions about a population based on information obtained from a sample of the population. Notice, here we particularly emphasize two words, population and sample. The major goal of inferential statistics is to extend the knowledge gained from sample to population. The methods include point estimation, confidence interval, and hypothesis testing. They are the main topics of this course. Look at the formal definition for population and sample. Population means the collection of all individuals or items under consideration in a statistical study. Population can be people and can be anything else. It depends on the purpose of your study. A sample is just a portion or a subset of the population from which the data are collected. This diagram shows the relationship between the population and a sample nicely. In practice, we always want to get information directly from the whole population. However, it is usually too expensive and time-consuming. Therefore, what we can do is to take a sample, or a portion of the whole population. If this sample is well chosen, the knowledge we get based on the sample is very close to that from the whole population. The census and survey illustrate clearly the population and a sample. The United States conducted a census every 10 years to acquire and record information for everyone living in the United States. The information is comprehensive but costly. There are many small-scale surveys to collect timing and detailed information from a representative sample, because we cannot wait every 10 years to collect information. The current population survey is a monthly survey of 50,000 households. The Bureau of Labor Statistics uses the data to provide a monthly report on the employment situation. This report provides estimates of the number of unemployed people in the United States. You can see that the unemployment rate reported in newspapers is essentially calculated based on a sample. However, there are many statistics behind the scene, including how to draw a sample, how to calculate the rate, and how to assess the variability and the reliability of the result. All those efforts are used to make sure that the calculated unemployment rate is very close to the true unemployment rate of the whole US population. Let's look at more examples to illustrate the concepts. This table displays the voting results for the 1948 presidential election. From the table, we can find the number of votes and the corresponding percentage for each candidate. Notice that this study is conducted on the whole US population, or at least all US adults who voted. Although the numbers are about the population, this study is still descriptive, because there is no inference. The purpose of statistics in this example is purely to summarize the information we collected. We can see that to tell whether a study is descriptive or inferential, the key is to check whether there exists both sample and population. A descriptive study can be conducted on a sample. It can also be conducted on the whole population. Let's look at another example. In 1977, the major leagues switched their baseballs from one company to another company. The pitchers began to complain that the new balls are livelier than the old balls. In a study conducted by Sports Illustrated magazine, 85 baseballs were randomly selected from the current supplies. These baseballs were measured for the bounce, weight, and hardness. Those measurements were compared with the similar measurements obtained from baseballs in the previous years. In the conclusion, they said that the 1977 baseballs are livelier than the 1976 baseballs. This study is inferential. The sample is the 85 baseballs selected. The population contains all the baseballs in the supplies. The goal of this study is to try to draw a conclusion for the all baseballs based on the 85 baseballs. In this example, we can identify both sample and population. The purpose is to extend the knowledge gained from the sample to the whole population. In fact, descriptive statistics and inferential statistics are interrelated. A descriptive study may be performed either on a sample or on the population. The main purpose is to summarize the data. And an inferential study always starts with a descriptive study on a sample, because we need a descriptive study to summarize information in a sample. Usually, the descriptive study on the sample will help us decide how to choose an appropriate inferential method. We should always remember that an inferential study is to extend the knowledge in a sample to the whole population. It involves both the population and a sample. There are different ways to classify a statistical study. Sometimes we may classify a statistical study by whether or not the researchers influence the subject under study. In an observational study, researchers simply observe characteristics and take measurements. Researchers will never try to influence or control the subjects in any way. A typical example is survey. You may send out questionnaires to people. What you want to do is only to collect information from them. However, in a designed experiment, researchers will impose treatments and controls on the subjects. In this type of study, researchers will intentionally influence or control the subjects. Observational study can reveal only association, but the designed experiment can help establish causation. For association, we mean something happens together. For example, when a kid grows up, his shoe size increases, and his math skills also increase. The shoe size and the math skill show a relationship of association, but no one believes that the shoe size is a reason for math skill or the vice versa. Clearly, they have no causation relationship. The shoe size and math skill increase together, but both of them increases as the kid grows up. However, in practice, people may not realize the difference between association and causation and draw a wrong conclusion. Let's check a new story. Pellagra is a disease. Pellagra was first observed in Europe. It was an important cause of ill health, disability, and premature death among the very poor inhabitants of the Austrias. Based on some observational study, scientists find that sanitary conditions in these diseased households were primitive. Flies were everywhere. It was also found that one type of fly had the same geographic region as pellagra. The fly was most active in spring, just when most pellagra cases were developed. It seems that there were enough evidence to show the association between pellagra and flies. Can we conclude that the disease was infectious and was transmitted from one person to another by insects like flies? The truth is that we cannot. Starting around 1914, Joseph Goldberger showed by a series of studies that the pellagra is caused by a bad diet and is not infectious. The disease can be prevented or cured by food rich in niacin. Niacin occurs naturally in meat, milk, eggs, and some vegetables and certain grains. However, corn contains relatively little niacin. In the pellagra area, the poor ate only corn. The flies were a marker of poverty, not a cause of pellagra. You can see in this example that association is not the same as causation. Let's look at an example of designed experiments. Scientists want to know whether folic acid reduces major birth defects. A study enrolled more than 4,000 women. These women were divided randomly into two groups. One group is called the treatment group, the other group is called the control group. In the treatment group, women will take folic acid daily, and in the control group, they do not take folic acid. Based on this study, there is a dramatic reduction in the rate of major birth defects. The rate in the treatment group is 13 per 1,000, which is much smaller than 23 per 1,000 in the control group. This is a typical example of designed experiments. Researchers will decide who take folic acid and who not. A designed experiment does help establish causation. What is a double-blind experiment? In the previous experiment on folic acid, the control group will also receive a pill, which looks like the same as the pill the treatment group gets. The only difference is that one contains folic acid and the other does not. By this way, the participants do not know whether she is in the treatment group or the control group. In fact, the doctor does not know either, because we do not want the doctor to give the participants any hint. Such an experiment is called double-blind. The participant does not know, and the doctor also does not know. Only the researchers know. Why do we need a double-blind experiment? It is related to psychological effects. If you do not feel well and see a doctor, the doctor may tell you that your condition is normal, don't worry. Even if the doctor does not give you any medicine, you may feel much better. This is due to psychological effect. In a designed experiment, in order to get rid of such psychological effects, participants will usually receive something similar, which is called placebo. Double-blind experiment is common in medical clinic research. Since we are talking about designed experiments, we have to mention medical ethics. This is a true story. The Tuskegee study of untreated syphilis. The purpose of the study was to observe the natural history of untreated syphilis. By 1947, penicillin had become the standard treatment for syphilis. However, the Tuskegee scientists continued the study without treating any participants. This study was terminated in 1972 after a leak to the media. This is a lesson to all scientists. In movies, there are always some crazy scientists, but in reality, it is not allowed. Before a study is allowed to start, we need to check whether it follows medical ethics. During the study, we also need to check regularly whether things have changed, particularly for those studies lasting for many years. In the Tuskegee study, the scientists should terminate the study immediately after penicillin became the standard treatment for syphilis.